And okay, sorry, this is this. Okay, ma'am. Can you see the whiteboard, all of you?
Yes,
And
sir.
Yes, sir.
yeah. So, any questions that you have? Essentially, what we were doing was we defined two things. We defined a mass action ratio which is the actual values of the products and the reactants. So if for example we have let us say 2A plus, I'm putting a random number here, and this is the elementary mode of reaction, is equal to say C plus 4D, something like that. And this is the elementary mode. This is obviously very unlikely to happen. This is just for illustration purposes. And this is the elementary mode. Then the kinetic order with respect to A is 2. The kinetic order with respect to B is 3. So the V forward is some K forward, or the V forward K something, let us say call it K1 into A square B cube, and the V reverse is some K2 C D raised to 4, right? You understand this, right?
Yes, sir.
And so the net rate of reaction is obviously V forward minus V reverse, which is equal to 0 at equilibrium. Which of course tells us that K1 A square B cube is equal to K2 C D raised to 4. So K1 by K2 is equal to CD raised to 4 divided by A square B cube. That is obvious, right? And so the mass action ratio, what is the mass action ratio here? The actual values of A, B, C, D present. And what would be the mass action ratio? Okay, first of all, tell me what is the K equilibrium. That is very obvious. What is K equilibrium?
A C to the power 1.
C D raised
D
to
to the
4.
power 4. Yeah. A square B cube.
B cube. This is K equilibrium, and obviously the mass action ratio is obvious from this. What is the mass action ratio? The value of gamma will be the actual C. This is at equilibrium, when there is no reaction taking place. And the actual values of C D raised to 4 divided by A raised to 2 B cube will be the actual mass action ratio. And from there we define something called and this K equilibrium is obviously equal to K1 by K2. Right? That's obvious. Because this into this is equal to 0. And this is the mass action ratio. And the rho, what is the rho? Rho is nothing but gamma upon K equilibrium. Right? And from there, you can actually do some very simple kinetics and prove that the V, the velocity of reaction, will be equal to the V forward into 1 minus 1. This kind of derivation you can do, this kind of maths you can do. This is simple algebra. Okay, so this is what I was trying to do. Yeah. So let us now, and of course, please also remember that the K dissociation constant. For example, I talked about HA going to H plus A, and I would like you to think about it. Right? And suppose, and this is the other thing that I said, and I said, therefore, x upon 1 minus x. And I want you to think about it. Why I wrote 1 minus x, and not something more complex. This is of course for the special case when there is a lot of water in the reaction and so on and so forth. And then we could sort of derive X as equal to K equilibrium upon 1 minus K equilibrium. That is what I did, right? 1 plus K equilibrium. Anyway, so now let us sort of, yeah, so I will just rub this out and we get back to the actual thing. So really now, before I begin, again, as I said, some few things out of the way, one or two very basic concepts which have a lot of similarity with enzyme kinetics. One, of course, is the whole issue of membrane permeability. And you are all familiar with this whole formulation of diffusion coefficients and the film theory. So membrane permeability also relies on similar concepts, where essentially the diffusion rates, or just like and therefore membrane permeability is essentially the diffusion coefficient across the membrane into ds by dx. Remember this kind of formulation? Fick's law of diffusion.
Yes, sir. Yeah.
And okay, sorry. I again have to switch this off. This has started giving trouble right away. Can you see it? Which is by definition. And then we say that we do not know what is this dx, so we call this as delta, and we combine dA and delta into some film theory, right? And we write this as some either we remember in mass transfer we used to write it as JDS, and for permeability we write it as P into ds, permeability into ds, where ds is the differential between. And so I will not get into these things, but I hope you remember this as sort of just as a quick reminder that permeability can be done exactly in the same way as you do the film theory of mass transfer, where the dx is the imaginary film across which the resistance lies, and therefore dA by delta is nothing but the permeability of the membrane, because we do not know the thickness of the membrane and we do not know the diffusivity. So these are lumped parameters. dA by delta is P, and ds is the actual differential of the substrate across the membrane. So P has to be calculated. So permeability into delta S is the flux across the membrane. We are familiar with this kind of formulations. And of course, similarly, the other thing that we have already talked about in the lab practicals, the effect of temperature, where essentially we keep on saying that the first order reaction is essentially whatever ds by dt is equal to ks, but k, the value of k itself is a function of temperature, which has an Arrhenius dependence, which is a e raised of minus delta E by RT. You're all familiar with this stuff, so I'm sort of quickly sort of getting this out of the way. And therefore, the plot of ln k, which is equal to nothing but ln A minus, sorry, actually plus, right? This is plus. Yes, plus E by R, delta E by RT. So a plot of 1 by T versus ln K will get you the value, the slope of delta E. And that is the activation energy. And what we keep on saying is that in catalyst, this is your essential function and this is your activation energy. And what happens with enzymes is that this activation energy becomes lesser. That is what the catalyst does, right?
Oh, yes, sir.
And so if you have a reaction B, as I said, if you have a reaction B equal to say K1A, and it's forward and backward. Remember that the catalysts do not change the equilibrium concentrations. This remains the same because the catalyst would increase both the forward and the backward reactions by an equal amount. You are familiar with that. And so the catalyst, if it is an enzyme E, then some E may not be necessarily the concentration of the enzyme, but proportional to the concentration of the enzyme, you just have a multiplying factor E. So the velocity will this will also increase by E times, and this will also increase by E times, where E is a function of E, the concentration of the catalyst or the concentration of the enzyme, and therefore the velocity actually just increases proportionally. So obviously it does not change at equilibrium when this term is 0. Because this, remember, is nothing but V forward into 1 minus rho. So at rho is equal to 0, the catalyst has no effect, because at rho equal to 1, sorry, the catalyst has no effect because the net reaction rate is 0 and does not change. So the equilibrium concentrations are not changed, but both the forward and the backward reactions are increased proportionally. So E is just the multiplying factor. And so if the forward reaction is fast, it will become faster when the catalyst is in large quantities.
Yes,
Right?
sir.
All of you are familiar with this stuff? Yeah. So now
Yes, sir.
we will.
Sir,
So
in
we
case
will
of
now.
enzymes,
Yeah.
like in case of enzymes, also like this like forward reaction and backward reaction, that constant doesn't change.
No, obviously not. Enzyme is a catalyst. So all rules of catalysts apply to enzymes, which means that they cannot change the equilibrium. They cannot, enzymes cannot, no catalyst can change the equilibrium conditions. The equilibrium conditions, we are dealing with kinetics. We are not doing thermodynamics. The delta G is what determines equilibrium. I showed you the ln rho versus that plot, right? Remember that plot?
Yes, sir. Like I asked the question just because like enzyme have a like different mechanism of catalyzing, different than normal catalyst.
Joby, whatever they can do, you can do whatever hell you want to do with methods of catalyzing. That will always only change this activation energy. But the delta G is given by these two terms. That this delta G, this cannot change. Actually delta H, but that's all right. This cannot change. This is by Hess's law, you cannot change A and B. This is here. So if you reduce this, then the backward reaction and the forward reaction would both get accelerated. If this was originally this, and now it became this. As you keep on lowering the activation energy, both the forward and the backward rates change. But the equilibrium does not change between A and B. Okay? So you cannot actually change the equilibrium condition, whatever happens. So these are very basic concepts, but sometimes it is good to revise them because you tend to forget. So whatever you have been taught, remember that those fundamentals in class 12th and 11th and 12th stand the test of time. So catalysis means equilibrium is not impacted by definition. Okay. So now one more important concept I think I should introduce, just like I introduced the concept of rho and mass action kinetics. So this is all sort of essentially very, very brief background to the stuff that I've been teaching. And let us now, and this is also something you might have done. You have heard of elasticity coefficients, right? Have you heard of elasticity coefficients? Elasticity of reactions? Elasticity coefficient, yes, no?
No, sir.
No. Okay, so then we should teach this. Now, this is a very important concept, especially in not just in enzyme engineering, but as I was telling about relaxation times, having applications all over the world in lots of modeling, not only bioreactor or bioprocess modeling or enzyme kinetic modeling, but also in a lot of modeling where the whole time window of observation determines what reactions you observe and what reactions you don't. Similarly, elasticity coefficient is a very interesting concept, for example, in systems biology, but in many other subjects as well, which is really, remember that the cell has a lot of reactions going on. There's a whole network of reactions going A to B and to C to and B going somewhere and A going somewhere, and I mean there are literally thousands of reactions going on, right? And really the cell tries to achieve what is called homeostasis. You're familiar with this term, right? Which is that some kind of steady state which is most beneficial to itself. Now, suppose there are fluctuations. Suppose there is a fluctuation in B, or suppose there is a fluctuation in the, so these are A, B, C, D. I hope you know that in networks theory, these are called the nodes and these are called the edges. Right? These are the nodes. And I do not know. Have you done many metabolic engineering or network theory? No,
no,
yet.
but like these kinds of things come in electrical.
Yeah, you will do this later on. I'm sure you should, because this is not the course to handle this. But later on, systems and synthetic biology, which is really the field that is of interest in biotechnology. So we try to understand networks in terms of nodes and edges, and we do various kinds of linear algebra that is applied, graph theory, which is sort of which is supposed the graph theory theoretic approach can help you understand these networks in a very simple way. The maths of graph theory is very well worked out. So what kind of reactions happen? But really, those are all steady state homeostasis models. But we here are interested in kinetic models. As I said, the far more interesting but much more difficult idea is the kinetics or the dynamic modeling of these networks. And one of the things, so therefore there is something called metabolic flux analysis, which is the steady state model. And there is something called metabolic control analysis, which is more difficult and not so easy to apply, which is to do with the kinetics or the dynamics of these systems. What happens when this concentration of enzyme changes or this concentration of this metabolite changes? What happens then? How do these fluctuations travel across this network and disturb the network? So really the question is, if you want to change a certain enzyme, what would happen? How much would the concentrations here change? Now, suddenly in the first step, obviously, if this is increasing, this would increase. So you would assume that this concentration would go up. But then this is connected somewhere else. And this is connected here, and so on and so forth. And as this reaction rate goes up, remember that this concentration will decline. So maybe finally your final endpoint concentrations of this fellow may not change very significantly, even though the enzyme has increased. So really what we need to understand as a first step, before we do get into complex graph theoretic approaches or whatever, we are not interested right now in doing those graph theoretic approaches, is to understand how does the reaction rate change when I change something. When I change the substrate concentration, when I change the enzyme concentration, when I change the product concentration, and this is a forward-backward reaction. So we need to understand what is the fractional. So we need to understand when there is a change in reaction conditions, what is the change in the reaction rates, right? We talked about, and so really what we are interested in, what is the fractional, and remember we're talking of fractional change, or rather I should call it percentage change. Let us put it as simple as percentage change in reaction rate divided by percentage change in the component of interest, in whatever you want to change, right? In say enzyme or reactant, let us say I will write as reactant, in reactant. So if there is a percentage change in reactant, 1% change in the reactant, what is the percentage change in reaction rate? That is the elasticity. Okay, so the elasticity is a measure. So elasticity, we write E like this, and we say velocity, how much does it change? So this is the thing that is changing here, this fellow here in the numerator, the percentage change in velocity. And if it is a reactant, let us say it is a substrate, we call it EV by S. Okay, so percentage change in reaction rate divided by percentage change in reactant is the definition of elasticity. Okay, so what are we saying? We are saying the percentage change in the rate of reaction will simply be given by dVi by dSi, isn't it? The fractional, but this is not percentage change. This is the amount of change. Now the percentage change is actually dVi, sorry, dVi by Vi. And the percentage change in reactant is actually dSi by Si. So actually this divided by Vi by Si, and Vi actually is because we use it in systems biology, so there are many reactions and many substrates, is actually the elasticity, dVi by Si. So the percentage change in the reaction rate divided by the percentage change in reactants will be given by this expression here. Let me stop here for a second, pause, and say, do you understand what I'm trying to say here? So the elasticity is a measure of the change in the reaction rate divided by the change in whatever component is participating in the reaction. I could also define elasticity with respect to enzyme concentrations. EVI by, so the it will be EVI, EV, let us say, by I here, by the enzyme concentration. Oh. Can you hear me, all of you?
Yes, sir.
ये तो अभी भी नहीं चल रहा है. You still hear me? Yeah.
Yes, sir.
With respect to enzyme. In which case, this one here, EV by E will be equal to dV by dE upon V by E. Right? So this is the definition of elasticity. Okay, so the elasticity of a reaction with respect to its substrate would be given by this expression here. And I hope you remember your maths. I mean, I never try to go into advanced mathematics. I don't remember it myself. So this here is also equal to, this expression here is also equal to what? Looks familiar? D of ln V by D of ln S. Correct?
Yes, sir. Yes.
ये तो आप लोगों को याद होगा, हाँ? Now this log formulations, because this is dV by V is ln V and ds by S. Sorry, उल्टा करना पड़ेगा. Sorry, this dV by V upon, so it is essentially dV by V by upon ds by S, and so this is equal to this, right? So they are all equal. So this formulation often helps in simplifying calculations. ये easy formulation है ना. Log लेने से मतलब जितने power equations वगैरह होते हैं, they become much easier to handle. So let me
Sir, I have a theoretical question.
Yeah. So let us go slowly. And let us say, let us take the simplest case. I mean, let us begin slowly because I know that you might have forgotten all this stuff. So let us take B is equal to K.
Question.
Sorry, go ahead.
Sir, the question is like you mentioned that like the cell wants to establish a homeostasis. So like
Yes.
a cell want to stabilize itself. Again,
Yes.
the thing is that if cell completely stabilizes, like it becomes like equilibrium stabilizes there, then the cell will like no more be called as living. So like what the cell wants to do.
आप लोग तो बहुत confused लोग हैं. ये तो बिल्कुल अब फर्स्ट ईयर मास एंड एनर्जी बैलेंस में मैं आता हूं. देयर आर थिंग्स कॉल्ड ओपन सिस्टम्स, रिमेंबर, व्हिच एक्सचेंजेस मैटर एंड एनर्जी विद सराउंडिंग्स, एंड क्लोज सिस्टम्स.
Yes, sir.
Right? You remember? And all living systems are open systems. ये सब चीज मैं नहीं पढ़ाऊंगा भाई, ये सब मेरा काम नहीं है. All biological systems are open systems, right? And so in open systems, the basic equation is accumulation is equal to input minus output plus minus reaction. Steady state implies accumulation is zero. Only in closed systems where these terms are zero, in closed systems these terms are zero, closed systems, will it imply that steady state or homeostasis means reaction is zero. This is the implication. This is zero, but this is zero only when in a closed system where input and output are zero. But in open systems, biological systems, you can reach homeostasis or steady state. Steady state is not equilibrium. Steady state is equilibrium only in closed systems. For open systems, steady state can be far from equilibrium because input and output are different. And therefore, input minus output plus minus reaction is equal to zero is homeostasis, steady state. And for open systems, that does not imply reaction rate is equal to zero. As a very simple example, in biology, now this is the chemical engineering approach. The biologist will tell you that here is the glycolytic cycle, glucose to tata. मुझे तो भाई साहब याद नहीं रहता ये सब चीजें. Pyruvate, है ना? And then onwards to the acetyl CoA and the TCA cycle. ये याद है आप लोगों को थोड़ा बहुत? याद होगा थोड़ा बहुत. And pyruvate also goes to various other things like acetate, etc. And this is the EMP pathway. Now pyruvate is in a steady state. The concentration of pyruvate inside the cell does not change, but because the amount of pyruvate formed is equal to the amount of pyruvate consumed in the TCA cycle. Glucose is coming into the system. Glucose is getting consumed very fast. The EMP pathway is very fast. The glycolytic pathway, glycolysis is happening, and then this glycolysis generating pyruvate going to acetyl CoA. Oh, nothing is done. Acetyl CoA going into TCA cycle going to electron transport chain and generating NADH, etc., etc. Everything is happening. Pyruvate is a central molecule here. Its concentration is not changing. That does not mean it is at equilibrium. It is at steady state. You want all these reactions to be absolutely steady state because that is the most optimal. Understand? If you fluctuate pyruvate, it would like to come back to its original value. If you increase pyruvate, suddenly the TCA cycle rates will increase. This rate is slow, so slowly pyruvate will go back to its original condition. But how does the fluctuation play out? Yaad aaya? Or the chemical engineering formulation is much more elegant but theoretical. It allows that only in an open system, steady state implies accumulation is 0. A steady state implies this is equal to 0. Again. Can you hear me, all of you?
Yes, sir.
Yeah. So in open systems, the assumption that accumulation is 0 and therefore it is steady state does not imply that reaction is 0. Input minus output plus minus reaction is 0. So all biological systems are open systems. If you are a closed system and you have equilibrium, then yes, you are right. You become a closed system when you are dead. ठीक है ना? तो equilibrium is reached. Okay. अब जब मर जाते हैं तो खाना बंद कर देते हैं, सांस लेना बंद कर देते हैं, है ना? तो basically, then you're neither exchanging oxygen nor giving out carbon dioxide, not eating food, and so on and so forth. I will not go into too much detail. Okay. So therefore, please remember this, है ना? So don't get into any confusion. So you should remember your basic mass and energy balances and remember that we are working with open systems. And therefore, steady state does not imply equilibrium. Steady states can be very, very far from equilibrium. Yeah. So back to the original problem. So now we were saying that E V by S. And let us take the simplest case. V is equal to K. हमें बताइए इसका elasticity क्या होगा? ये तो बहुत simple सवाल है. So obviously, dV by dA is equal to K. Correct?
Yes, sir.
Yes.
Okay. And therefore what is it? And therefore what is the elasticity? V by S. ये कैसे define किया था हमने अभी? dV by, because it's now no longer partial derivative. dV by dA upon V by A.
V by A. Yeah.
Right? So this is equal to K divided by what is V? Ka upon A. That's equal to 1. Okay?
Yes, sir.
All of you with me till now? Right. So we can see, now let us take another case. V is equal to Ka raised to of N. 0th order, first order, second order, whatever, है ना? Nth order reaction. अब आप लोग please derive करिए इसको. Tell me what is EV by S? Please. So tell me.
N by
Don't derive it. Tell me. dV by dk क्या है?
N by K.
dV by dA is equal to
N K to the power N minus 1.
Nk A less than n minus 1.
Yeah.
So this EV by S will become equal to n k A minus n minus 1 divided by V, which is k A n upon A. तो क्या हो गया ये? What is EV by S? N. So notice, can you hear me?
Yes, sir.
Yeah. So notice that the elasticity coefficient E V by S is nothing but the order of the reaction. First order of the reaction. So notice that at first order it is equal to 1, at nth order it is equal to n, and so the elasticity coefficient is nothing but the order of the reaction. Okay, right? So now why is that? Also, I mean, I forgot about the other point. I mean, that is first point. The second point that I want to make here is that remember that we said V is equal to Vf minus Vr. And so this is in the positive sense. So when the reaction is going forward, remember that elasticity coefficient with respect to substrates will be always positive. Will be positive, greater than 0. Will be positive, greater than 0. And remember that elasticity coefficient with respect to product, if there is a backward reaction, will be negative. Does that make sense?
Sir, can you please explain again?
अब बताइए, आप सोचिए क्या होगा. चलिए इसके बारे में थोड़ा सोचिए. मतलब not everything should be, not every simple point should be explained. Now, let me sort of explain the other minor point here. I think every time I have to erase, which is not a good idea. So really, what is the graphical interpretation here of E? Let us say I have Michaelis-Menten kinetics and I'm not solving it deliberately. We'll solve it in a minute. And this is my graph. And at this point, let us say I want to find out E. E at this point. When substrate concentration is this value, so the real point is that when substrate concentration is this value and I fluctuate the substrate concentration, how much does V change? And for that, it is a simple task. I am going to take the slope here. This is dV by ds.
Yes, sir. And then V by S.
And then this is dV by ds. And then we will divide it by V by S. Now V by S is nothing but, I mean, this is a poor line, but मेरा भैया fail हो गया था उस exam में. क्या बोलते हैं? 101 art or whatever. Engineering drawing. तो ये ठीक है ना? So therefore EV by S, notice. So E is nothing but this tangent divided by this chord. Okay, so if we had finding out the value of V by S here, you will say this is this tangent divided by V by S, which is this line. The slope of this divided by the slope of this, because this is V by S. This line is V by S. And this is dV by ds. So can you make out now why in a first order reaction, EV by S is equal to 1? That becomes obvious, right?
Yeah, for that V and S, so the graph between V and S.
So V by S, yeah. So for a first order reaction, the enzyme kinetics is like this. This is V versus S for first order reaction. And obviously the tangent to any point and the V by S at any point will be exactly the same. So this here and the tangent here, that will both be equal, and therefore E will be equal to 1. Right? So,
yes.
so the more, yeah, and the more interesting point that I hope you realize from this, is the kinetics, Michaelis-Menten kinetics, is that unlike V is equal to K A raised of n kind of formulation where E was equal to n, in Michaelis-Menten kinetics E changes. It is here it is close to 1 and here it is much less than 1. Can you make out? So E changes. It is actually a function of the substrate concentration at which value you measure the V. And that is the interesting part of all biological reactions. So the fluctuation and the percentage change in fluctuation depends on the steady state value. Okay, and I will tell you later on why that is important at some point of time. So the fluctuation here will have an E value of 1. The fluctuation here will have an E value of close to 0. बहुत छोटा होगा, मतलब much less than 1. Okay, is this clear?
Yes, sir.
So can you derive it before we or shall we make general rules first, or maybe shall we make general rules? I mean, let us do little bit of arithmetic or maths, basic maths, and make general rules for determining elasticity coefficients using essential principles of standard class 11, 12 stuff differentiation. So really, let us make the general rules today. And I think how much time do we have? 15-20 minutes. That should be good enough, right? So you have y is equal to fx, right? And therefore, therefore we can say that ln y is equal to ln fx. Well, like this actually, to be fair, but yeah, do you follow this argument? Right. So what is and of course, dy by dx is nothing but what I'm saying is f prime x, right? Okay. And so 1 upon y dy by dx is equal to, you can see where I'm going here. Okay, are you following this?
Yes. Yes.
Okay, I mean, okay. Let us make it very simple. Let us make it obvious what I'm trying to do. Suppose fx is a multiplication of various functions as well as raised to power of something. So, I mean, I hope you remember this. Pi is the multiplication, right? Fx is a multiplication of various functions, fi, x, and let me sort of say again some alpha, which is a function of x, which is xi. Okay. Are you following what I'm writing here? And so we can say ln fx. I'm trying to find out the rule for multiplication. Basically, okay. This is too complicated, but what I'm trying to do is very simply, if I have say fx is equal to say gx into hx, sorry, too many brackets, but yeah, you understand. Gx into fx, then if I know the elasticity of this and I know the elasticity of this, what will be the elasticity of this is my question. Because now I can take, okay, इसमें ln fx करके आप इसको आप निकाल सकते हैं. What will be ln fx?
ln jx plus ln hx
will now become summation, right? Right?
Yes, sir.
Alpha I and alpha will come here. Alpha I x, alpha. Actually, yeah, alpha I didn't write alpha I, right? Alpha I x into ln fx. That makes sense to all of you, right? This is just taking logs, and so ln fx is nothing but उसको अगर हम derivative लेंगे तो f prime x upon fx, ठीक है, is equal to, then I have a summation alpha prime, of course, depending on what ln fxi plus this is u into v formulation, right? Plus alpha I x into, again now this will be f prime x upon fx. I mean I, of course, fx. Does this make sense?
Yes.
And so we can then, and then we can sort of write it as we can take out this thing outside and solve it. So I mean, I want you to sort of solve this, but I think I will not proceed too much with this. This is just obvious algebra and differentiation. But let us do it for this one. Let us do it for this one. Let us do it for a simple function like this, where there is no power, etc. Just a multiplication, u into v form. How will how does the whole conversion? See, instead of writing dv by ds divided by v by s, I'm trying to tell you that actually this d ln v by d ln s formulation is actually far easier to handle algebraically. You see, because of this kind of functions. This is what I'm trying to prove to you. And you will discover that actually working with logs makes it easier whenever you have this multiplicative function, or for example, fx is equal to, for example, is equal to gx upon hx, which is nothing but saying gx into hx instead of -1, alpha is -1, right? And gx is +1. So all these formulations actually become very, very simply equivalent to this. So let us do the simple one. Let us do this one, and you can extend this logic to more and more multiplications. This is the most general case. You could have gx, hx, ux, vx, etc., etc. It will become obvious when we do this. It's not a very tricky business. So so we are having. So what did I say? Okay, fx is equal to gx into hx. Now help me out here. मैं अपना differentiation भूल गया हूँ, है ना? So ln fx is equal to ln gx plus ln hx, huh?
Yes.
Okay. Okay. And therefore f prime x क्या होगा upon fx. Now notice that I will now multiply it by x. You know why I'm multiplying it by x? I hope you understand why I'm doing this. Because हमारा e का definition क्या है? It is f prime x e of fx. See, y is equal to fx, right? I mean, I hope. Am I going too fast or is it? So yes, y with respect to x है ना आपको? तो ये f prime x है upon y by x. Yes, which is nothing but f prime x upon y into x upon fx, sorry, the same thing, into x. So ये आ गया ना हमारा e. This is what become your e na of this function. So into x is equal to now I will write g prime x by gx into x plus h prime x upon hx. So you should help me out here. As I said, I have forgotten my differentiation and integration a long time ago. You will also forget when you reach my age. Okay. So okay. So what do we have here now? Therefore, come on, let us have some answers from you guys now. So what is? So this is what? This is E. This is an E of y, sorry, fx. Let me call it as fx. Let us retain the fx here up by x. Okay. And what is this equal to?
This is g of g and x.
This is, how is this related to E? This is nothing but E gx of x, right? Plus yes. E hx of x. See? So what we are saying is, if y is equal to u into v, then, and both of all are functions of x, then E of y with respect to x is nothing but E of u with respect to x plus E of v with respect to x. And I hope you understand that this was, if this was this divided by this, then ये plus की जगह minus हो जाता है, यहाँ पे ये minus हो जाता है ना, और यहाँ पे ये minus हो जाता है. And therefore, if y is equal to u by v, now see, you understand the advantage now.
Yes, sir. Now we can say like
इसको अब ये
it will be
irritating
negative.
ये irritating differentiation ना करके, if you can make I should definitely file a case against the computer fellow. If we had, can you hear me? If we have y is equal to u by v, then we can simply see that e of y with respect to x is equal to e of u with respect to x minus e of v with respect to x. So you see, multiplication division, because of the log nature of this differentiation, translates into this kind of formula. Plus when it is u into v, and minus when it is u divided by v. And this can be extended. U v w will be just plus y by w. So this makes life very simple. So multiplications and divisions of elasticities of functions translates into elasticities being added or subtracted. Okay? And that is why I wrote that. Now you realize what I was doing in the board which I wiped out. And then if it is restorer of n, you can also handle it. N1, N2, and so on and so forth. You saw that because n1 derivative, the first derivative of the one that I wrote, that will become 0. Because the alpha derivative, alpha prime will become 0, so the second function will disappear. Just now when I was writing about pi, all of you saw that? Hello?
Yes, sir.
You forgot. Okay. No. I just wrote one which I wiped out, the board which I wiped out. Okay. Yeah, so so that is it. So that is a very easy thing to do. And so that is, how much is the time left? 5 minutes. Okay. Now, unfortunately, the things are easy for multiplication division with log, but they become actually irritating for additional functions or subtraction functions. The fx is equal to gx plus hx. It now becomes irritating here because now we have ln of, because there's not much of manipulations that you can do with respect to ln of gx plus hx. There is not much manipulation you can do here. So let us do this. F prime x upon fx, okay, is equal to, बताइए क्या होगा? I hope you realize this, right? G prime x, because this is just summation, right? So plus h prime x, okay, upon the whole function gx plus hx. Okay, it's obvious, right? Ln of this is ln of this. So this is it. And then I multiply throughout by x again. I multiply both sides by x. So what do we get? This here becomes your e, fx by x. Now this side here is actually problematic because it is g prime x into x upon gx plus hx. And this plus, of course, h prime x into x upon gx plus hx. So now you see that the elasticity coefficient will actually be g prime x divided by gx by x. Right? This is what the elasticity is of E. E gx by x. Am I going? I'm going. Okay, right? Or is there some problem here? All of you are listening because I can't make out.
This is fine.
So what do we get here? So how do we simplify this? So we get this expression here, this fellow here. This part is E gx by x. So E fx by x is equal to Now you have to actually multiply and divide by gx, right? This is here. So you have to multiply and divide by gx because so into gx. So multiply by gx, divide by gx, and this division part gx by x upon x is actually, this is equal to e gx by x. और क्या होगा, बाकी क्या रह जाएगा?
gx
and
upon
both this term and this term will remain.
Yeah.
So this into gx divided by fx.
Yes.
Right? So we can see that therefore this function here will have a slightly irritating formulation, which will be given by, बताइए, this will be e of fx to x will be equal to e of gx by x into gx upon gx upon fx
plus
e of fx hx by x into hx upon fx. Okay, so when you have summations, the elasticity of this is equal to elasticity of this multiplied by this function itself divided by the total function plus the elasticity of this function into this function itself divided again by this whole function. Okay, and similar rules with subtraction. So let me sort of wrap this up by saying that therefore, so you saw the plus minus rule and the multiplication division rule, and therefore, for example, if we have Michaelis-Menten kinetics of V is equal to V max S upon Km plus S, you can actually derive it by first principles much more easily, but I thought I would sort of do this for you guys. Then this becomes, then the E of V by S becomes equal to first E of, now I will apply the rules, E of Vm plus S, sorry, Vm into S by S. Okay, मैं ऐसा करता हूं, इसको ये लैंग्वेज नहीं यूज करता हूं, मैं इसको लिखता हूं E of V, ये obviously with respect to S है, is equal to U by V form. Okay, so this is U, this is V. So this is E of VMS. This is the time it has to go off. Can all of you hear?
Yes, sir.
E of VMS minus E of Km plus S.
Yes, sir.
Okay.
Yes.
And this is equal to E of Vm plus E of S. And this is equal to E of Km plus S. Okay. Now E of Vm क्या होगा? What is E of Vm? Hello.
Yes, sir. It should be like 0 or 1.
It will be 0 because it's a zeroth order reaction. Na? E of Vm or E of S is first order reaction. So it is 1. Hello. Yes.
Yes, sir. Yes.
तो अब बताइए बाकी का क्या होगा? Km plus S का मैं नहीं करूंगा.
Sir, it will be like
1.
It will be.
चलिए आगे Km plus S का फॉर्मूला लगाइए. Minus, and this is E of Km. Oh, this is why I don't want to complete this. Can you hear me?
Yes, sir.
E of Km into Km upon Km plus S.
It will be
And this will be,
upon Km.
and then plus E of S into S upon Km plus S. Can you,
Yes,
are you
sir.
following this?
Yes, sir. Yes.
Oh, yeah. So now please simplify and tell me what is the answer.
Sir, E of Km will be 0. So this term will be 0 and E of S is equal to 1. So that will be S upon Km plus S.
ठीक है. So correct, you are right, absolutely. So what will be the expression? It will be E will be equal to
1 minus S upon Km plus S.
1 minus correct. So E will be equal to E of V by S will be equal to 1 minus S upon Km plus S. Right? All of you got this?
Yes, sir.
Right? Which is therefore E is equal to Km upon Km plus S. So I derived it using the formulas of log addition. You could have derived it directly also. It's not a very difficult job. You could have just taken the derivative but iska derivative nikalna or फिर divide करना, multiply करना, Km plus S whole square etc. If you do all that, if you use it by first principles, dV by ds upon V by S, you will come to the same result. I just sort of tried to show you that if we have general formulas, we can derive it by much simpler algebra. Are all of you getting this? Hello?
Yes, sir.
And do you realize the implications of this? So notice that when S is close to 0, E is equal to 1. And when S is much larger than Km, E is equal to 0. Which makes sense, right? Which makes a lot of sense.
Yes. According to
because
the
the graph of V versus S, V versus S is first order when S is very small and becomes 0th order when S is very large. And therefore, E here is 1 and E here is 0. And so you can see that this expression here reflects this reality that when S is very low, then Km upon Km plus S is nothing but Km upon Km, so it's close to 1. And when S is much larger than Km, very large, then Km upon Km plus S, Km is small, so it is 0 upon, so this tends to 0. So there is a tendency for E to move from 1 to 0 as S increases. Let us stop here. I think it's 10 o'clock already, and next class we will handle it. So these formulas are very useful to derive kinetics. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.